like to welcome everybody to IA to join this open house for the project we call BURSTT. So we'll hear more about it later. My name is Kayang Lee. I work here as a support scientist. The schedule is listed here. So we'll take a lab tour after our introduction and take a break at around 3:30, and we'll hopefully finish the talk by follow this discussion by 5 p.m. If you need Wi-Fi access, please look at the board there. Okay. First talk, I would like to welcome Tetsuya Hashimoto-san to help us give an introduction to the FRB. Okay. Welcome.
Okay, so thank you very much for this opportunity. I really appreciate Kanya leading this opportunity. So first of all, I think this meeting is dedicated to the new students. Therefore, in my introduction, so I make it easy as possible. So I hope all of you guys, including new students, can understand what I'm saying. So, but just in case, if you don't understand what I'm saying, please just stop my talk, and then you can please feel free to ask any questions. So, okay, let me get started. Actually, today's my talk is kind of summary of my previous lecture about the FRBs. Therefore, it is all recorded in YouTube. Therefore, if you want to know more about the details later, then you can just take a picture of this, and then you can just access YouTube video to know more. So, I am Tetsuya Hashimoto from National Johnson University. So, let me introduce the FRBs first. So this is an outline of my talk today. So first, let me start with introduction of introduction. So I will talk about a very basic but unique observable FRBs first. And then let me talk about a little bit about this origin of FRBs. Actually, probably I don't have much time to talk about everything, but let me focus on the localization. This is a really important function of FRB telescope. Then I will briefly explain the interesting, exciting applications of FRBs in future works. Then, if I have time, let me introduce how the new our radio telescope is important. So in the end. Okay, let me get started. So, as usual, usually I start with this video. So this is just a normal sky in optical wavelength, but of course you can switch to radio emission. If you see the sky in radio emission, it looks very different from that in optical. The most different part is, as you can see, there are so many flashing objects in radio frequency. So this is so-called fast radio burst. So if you go to very short time scale, there are so many new objects that no one noticed before. So this is really frontier of astronomy now. So this fast radio bursts are happening so many on sky, but we don't know the origin of fast radio burst. Therefore, revealing the origin of fast radio burst is one of the most important missions in astronomy now. By the way, this flashing object, I just artificially put it there. This is not real data, but I hope this will help you understand better about the FRBs. So FRB is something like this. And then this is a kind of artistic image of FRB, which is actually coming from extra galaxies. So there's a galaxy here, and then there's a source emitting FRB, and then which propagates all the way to our telescope on the Earth. And then the unique point is that this radio pulse is very bright, which is Jansky level. This Jansky level in radio astronomy is really bright. And the time scale is only millisecond. So this is very short. So therefore, this is really new in astronomy. Therefore, no one noticed this new object before. We just recently started to discover this interesting object. And now we have so many nature papers about FRBs. So therefore, many people start to pay attention to this fast radio burst recently. And currently, these radio telescopes, so for example, FAST in China, and CHIME in Canada, ASIAA perhaps in Australia, these telescopes are actively detecting fast radio bursts a lot now. And then, let me introduce very basic things about FRBs first. So this is a typical example of first FRB detection. So this is frequency in y-axis as a function of observed time. And then we do detect FRB in this way. So you see that there is line here, straight line here. So this is a typical example of detection of FRB. So it's really fast. It happens only within very short time scale. But one important point is this arrival time x-axis is actually different for different frequencies. So therefore we see that this tilt straight line here. So this is so-called dispersion measure. I will explain about dispersion measure. So this is a really unique observable of FRBs. So what is dispersion measure? So this is more like similar to something like a prism in optical wavelengths. So you know prism, right? So optical light, when optical light propagates within the prism, the speed of optical light changes as a function of frequency. Therefore, for different frequency, speed of light changes, right? Therefore, it refracts. And then you get dispersed optical light here. Then this is how prism works. And then this is in optical. But similar things happen in radio frequency too. So, when radio emission propagates in the intergalactic space. So this is a typical example picture of the sky. So you know there are so many galaxies in the universe. And then, actually, in between galaxies, in intergalactic space, so that is not empty. Actually, there are a lot of plasmas in intergalactic space. Then when radio emission propagates within the plasma, actually this dispersion happens. So for example, the speed of radio emissions changes as a function of frequency. So for example, high frequency radio emission actually doesn't affect very much. It can keep fast speed. But frequency is lower. Actually, the speed of radio emission change a lot. It becomes slower and slower. Then, let's say it happens at the same time. It starts to propagate, at different frequencies. But speed of light is different. Therefore, the arrival time of radio emission can be different at different frequencies. So this is a dispersion measure. So, for example, say FRB happens here, FRB1, at actually distance universe. And then FRB emission propagate from this galaxy to our Milky Way. So we are standing here. And then in this case, we have longer distance here. So that corresponds to more plasma in between galaxies, lying on the side to do this FRB. So that means you have longer time lag between different frequencies. But if FRB happens nearby universe, say here, FRB2, and then you have less amount of plasma in between observer and FRB. Therefore, actually, you have shorter time lag between different frequencies. So therefore, this time lag between frequencies actually depends on how much plasma material you have in between observer and FRB. So this is really unique. And then let me explain the same thing again in this figure. In more practical way, actually we do detect FRBs in this way. So as you can see, there are two lines here. This one, FRB1 is here. And then another one is here. So there are two different FRBs shown here. And then, for example, FRB1 case, that was more distant one, FRB1, more distant. So it appears something like this. So let me explain the same thing again. So for the fixed frequency range, for example, from this frequency to this red frequency, actually time lag becomes this time scale, right? So actually relatively, this is relatively longer. So that means longer time scale means you have more amount of plasma in between FRB. That corresponds to more distance universe. But if you look at the FRB2, this is a closer one, it appears something like this. So now tilt is different, you can see. So for the same frequency range, actually you see the shorter time difference between these two frequencies. So shorter time now actually corresponds to less amount of plasma. So therefore, this corresponds to nearby universe, very roughly speaking. So therefore, so this dispersion measure of FRB is really unique. So other observable sources cannot provide this information. So when we detect FRB, so more or less we can estimate the lab distance to that FRB. So this is so important and so unique of FRB. So this is, I think, important to understand before we go to the very details. This is, I think, also related to data analysis part. And then, next, let me talk about the origin of FRBs. So the problem is, we don't know what they are. So observationally, actually, it is known that there are two different types of FRBs. This is pure observation definition. So this is very easy. So one is non-repeating FRBs. So recently people say one-off event. So this basically seems to be basically. So this is say there is a galaxy here, and then there is a FRB source inside of this galaxy, and this emits FRB. If you detect only one time FRB from that source, we say this is non-repeating error because it's not repeating. It happens only one time. Then this is non-repeating error. And another category is repeating FRBs. So in this case, there is a same FRB source here, and then you detect multiple FRBs, say more than 2 FRBs are detected from the same astrophysical source. And then we say this is the repeating FRBs. So this is really observational definition. Anyway, so if we count the currently detectable FRBs and then extrapolate to the whole sky, and then actually more than 1,000 FRBs are happening on sky every day. So this number is really a lot. The problem is, even though we detect so many FRBs for now, but their origin is still unknown. So we really want to understand what they are. And then from theoretical works, actually there are so many theoretical models have been proposed so far about FRB origins. And then I selected here possible candidates of FRB progenitors. So progenitor means the astrophysical source that can emit FRBs. I mean, in short, origin of FRBs. And then the possible candidates are, say, white dwarfs, all the neutron stars, all the stellar mass black holes, magnetars, young pulsars, supermassive black holes, or supernova nebulas. Probably more than these, but I just selected the majority of the possible candidates here. The thing is, there are so many progenitors here, and we really want to differentiate. So which is really the origin of FRBs or not? We really want to separate them. But problem is, we don't know. So this is really what we want to understand. The question is, how can we identify the progenitor? How can we identify the origin of FRBs? So one most reliable way is actually localization. So let me explain this idea. So localization, I think, is really important to understand when we talk about the class project. So what is this? So this is again the picture of sky. And the current situation of FRB observations is something like this. So we detect FRB. Okay, we want to know where is the location of this FRB. We detect FRB. And then positional uncertainty, positional error of FRB is something like this on sky. So for example, CHIME. So this is really powerful radio telescope that is detecting many FRBs now. This is the kind of most powerful survey FRB telescope. But in CHIME's case, for example, the positional error on sky is something like this. So we know that FRB came from somewhere within this circle, but we don't know where it is exactly. So this is the problem. It may come from this galaxy, or it may come from this star, it may come from this one, or this one, this one. No one can tell it. So this is a problem when we try to understand the origin of FRBs. So this is a problem that we are facing now. Ideally speaking, most reliable way is localization. So what does this mean? So localization is you measure the location of FRB very accurately on sky to identify the astrophysical source that emits FRBs. In this case, if we can make the error smaller, as small as this one, so there is only a single astrophysical source within this error circle. So that means we are sure that, this FRB came from this astrophysical source. So this is really powerful because you can directly identify the progenitor of FRB using localization. So this is localization. This is really powerful if we can do this. However, actually technically this is not easy because as I mentioned, the time scale of FRB is millisecond only. Then within this short time scale, you need to really localize FRB. This is technically difficult. Therefore, this localization case is really limited for now. Only one successful case that I can show is here. So actually, in 2020, there are very bright FRB, and then actually 3 telescopes detected this bright FRB at the same time, and then each telescope has different positional errors. For example, STEAR 2, this has huge positional error, which is shown by blue region here. So there is no way to identify progenitor only from these observations. But at that time, this FRB was too bright. Therefore, China also detected and then localized down to this size. And then first, this is Chinese very big telescope, radio telescope, also detected at the same time to accurately measure the position of this FRB on sky.
Yes, I'm
Yes.
afraid fast telescope didn't see this first.
No, they detected.
Detected
Oh, no, yes.
later?
Yeah, yes.
The same first April first.
Yes.
Oh, yeah.
It's written in paper.
Oh, yeah.
Oh, yes. So actually, this was necessary to really localize this event. Because China only cannot localize the levels.
Yeah.
It's written. Yes.
Thanks.
And then, actually, I was wondering the same thing. It's written also. So therefore, in this case, so using 3 different telescopes, they were able to localize this event. And then later, they found that there is a galactic magnetar. So galactic means there's a magnetar inside our Milky Way. So they found magnetar at this location. Therefore, for particular this event, now we know that this FRB came from this magnetar. So we know the origin of this FRB. The problem is the successful case in terms of revealing the progenitor is only this case so far. Then now we have more than 600 FRBs detected. Then we don't know anything about other 600 FRBs. So this is a huge problem. So maybe I don't have time. Take 1 more minute. 2 minutes. 2 minutes. Okay. So, and then let me explain. I think this is a more important thing to me. This is about FRB origins, but more importantly, I personally think FRB is really unique in astronomy. So I would say FRBs are really special in astronomy because this is probably only the astrophysical sources which will allow us to address so many key sciences in astronomy and astrophysics. So for example, missing variant problem, general relativity, dark energy, cosmic reionization, dark matter. So all of these things are key sciences in astronomy. And FRBs are expected to allow us to address these key sciences in astronomy using the unique observer. Therefore, if you can solve one of them using FRB in the future, you may have a big chance to receive a Nobel Prize in this FRB field. Therefore, now we have to work on the FRBs. And then it's come to BURSTT project. So now in Taiwan, we have a big chance to lead this FRB science in the world using our unique radio telescope of BURSTT in Taiwan. So I have to stop here. Okay, thank you very much.
So I have a question. So if we have poor ability to localize the FRB, how do we constrain the local density of the plasma at the source.
Okay. Actually, so that means in terms of line of sight direction, we still have the uncertainty error. So line of sight, I mean, what we measure could be along this line of sight or this line of sight. We have this uncertainty. So along the line of sight object. So we can only tell the one point along within this sample is measured this value.
So if we use DM to measure the distance, then how do we constrain the source, the source contribution?
Oh, that's a very good question. I think that's much more than I thought. Yes, you are right. So plasma is actually not only in intergalactic space, but also in, as you know, so in galaxies or host galaxies or in our Milky Way. And then for Milky Way component, actually it is possible to kind of subtract because so we have many pulsar observations already for our Milky Way, and then therefore sort of we already know the dispersion measure contribution from Milky Way along different line of sight. So there's already model. That is still model, but kind of we can subtract using that model. And the problem is the FRB host galaxy side. So the galaxy hosting FRB should also have contribution to dispersion measure because there must be plasma in that galaxy. So this component is really difficult to subtract. Therefore, what we can do now, best effort is we kind of assume the typical number from, for example, simulation or something like that, or observations. Actually, you can kind of estimate. Therefore, we need to assume that number to subtract.
Sorry, let me say, regarding the fast localization, I'm very sure fast didn't see this burst at the same time. What fast saw is the activity, radio activity, after, so people after getting burst by STR2 and also China telescope, they have a rough localization. Within this region, there is a one supernova remnant, which is hosting galactic magnetar. That's why past telescope watch this more deeply by pointing observation. Then fast reveal the most kind of the faintest radio burst.
Okay.
So didn't see this
not the same one, but burst at different times.
Yes.
Okay,
Pulsar emission.
Good.
Yes, so but it's not FRB.
Really?
So because it is important because this is localization. Yes. So I'm sure.
Okay, thank you.
By the way, what is the apparent size of this circle?
I draw just very roughly, but for Chinese case, it really depends. But typically, it's 8 arcmeans radius. Arcmeans level.
Okay, there is no other question. We'll switch. Thank you. Okay, so in this talk, I'll talk about the first project, its design and its goal. Okay. So we have recently put our project overview paper in archive. So later on, if you are interested, you can look for more details in this paper, which is led by Xiuxian. Okay, so as Tetsuya mentioned earlier, so the key to the current stage of FRB observation is localization, and also to find to cover the wider sky to find more candidates. Because if your telescope can only look for a very small patch of sky, as you know, FRB doesn't always stay there. It's intermittent if it's repeating. So if it's repeating, but you just missed it when you're observing somewhere else, then you don't see it, or maybe you saw this one-off event when it's actually repeating. So increasing the field of view is actually also an important part of the observing requirements. And since the discovery of FRB in 2007, in the first 10 years or so, we only discovered a few tens of FRB. But with Chime, there is an order of magnitude more FRB found after a couple of years of operation. That's precisely because Chime has increased the survey area compared to other traditional radio telescopes. So these two key, so there are many projects which is trying to realize these two key points for the new generation of FRB observation, including like CORD, which is an expansion of Chime by adding several outrigger stations that can do VLBI to localize the event, or HIRAX, similar event with a large number of small antennas to increase the field of view and localize the source. And also our own project first. So in our case, our telescope is different from these other telescopes in that we don't have a reflector antenna at all. We just use dipoles to collect the signal, which is similar to the low frequency array of the SKA or something similar. So this kind of aperture array is also very suitable for finding FRB. Okay, I'll do the next one. So let me first give you an idea of what Chime is, and later on you'll see why ours is different. So Chime is originally a cosmological experiment trying to looking for the neutral hydrogen in the universe. So it's designed to work in 400 to 800 megahertz. But it has a unique design in that it has a cylindrical reflector. So the size is about 100 meters by 20 meters for each cylinder. And there are 4 cylinders in total. So its original idea is to map large-scale structure of H1, and it's been recently have some results published which say when they cross-correlate this H1 signal with galaxy distribution, they have positive detection of the H1 distribution. So for people who are interested, we can check out more details. Yeah. But in our case, we are more interested in its expansion to find FRB. So for cosmological application, you only need to integrate a long time to reduce the noise. But for FRB, you really want a millisecond or better time resolution to find this really fast bursts. So for this, they expanded the backend for Chime. And there are, for each, there are 256 receivers in each of the cylinder for one qualization. And for each one, there's 400 megabytes of data. So in total, raw sample size is about 800 gigabytes per second. So you can imagine it's, a lot of data is coming in real time. You have to find ways to process. And therefore, they have dedicated computing resources to process all this kind of data. So what I want to show here is that all this kind of challenging that birds will face is actually something that has been realized before. So it's something new to us. We need some, we're not so experienced yet, but should be something that's, I mean, the design from Chime is about 10 years ago, so everything should be much more powerful now. It's our job to make it happen. Okay, so about the design of Chime, when they use cylindrical reflectors, that means for each receiver on the this feed line. It has a beam function like this. In the east-west direction, there's some confine, which is about 2 degrees wide. But in the north and south direction, there's no focal focus. So the beam size is about 100 degrees in north and south. So in total, they have about 200 square degree field of view for each receiver. You can see all the signal from this 200 square degree strip on the sky, everything. So in order to find out exactly what region of the sky is contributing to your signal, you have to combine the signal from all the receivers on the feed line, and then also combine the receivers from other antennas. So in this cartoon, there are only maybe 20, they use only 20 feed receivers on this feed line. And when you combine these phase of these receivers, you can actually construct 20 beams on the sky in the north-south direction. And when you combine with 4 antennas, you can do the same thing for 4 beams on the east-west direction. So in reality, because there are 256 receivers along the north and south direction, so there are actually 256 in the north-south direction on the sky as well, and times 4 in east-west, so 1,000 beams on the sky. Each beam is roughly, I think, 0.5 degree in size, so 15 or so. Sorry, almost 30 million in resolution. So it's much better than no beamforming at all, but it's still relatively poor on the sky. You still cannot know which galaxy is responsible for this FRB signal. So for that to work, you really need a telescope that's far away, like hundreds of kilometers away, in order to better localize source. And also another point is that this kind of telescope, they are fixed to the ground. So their beam, you can design a beam on the sky, which is also stationary. It doesn't change with time, but the sky moves across the beam. Then, so you can find objects that happen to be in your beam, and you can detect it. It's important if we can enlarge this field of view, then you can have a much better chance of finding rare objects, or intermittent objects. Yeah, so there are 1,000 beams for the time, and for each beam, we also need to design that how much in dispersion measure we want to search. So all this contribute to the computing requirements. So this will come to this part a bit later in today's talk. But it's called a scalable design because unlike a full like ALMA type of radio telescope arrays, which you have to do cross correlation from all antennas. If that's in that kind of design, the computing complexity is about n squared. So if you want to do 2 times larger experiments, you have to do 4 times. You have to invest 4 times more in correlator. But in this kind of telescope, n times more telescope collecting area just means you have to do n times more computation. So it's more manageable. And when we have resource, we can expand the project, scaling. Okay. So this is the first project overview. So we call it Bustling Universe Radio Survey Telescope in Taiwan. So many radio objects out there. It's bustling universe. And our design is that we have a main array consists of 256 antennas somewhere in Taiwan. And then some outriggers in Taiwan with 64 antennas or maybe in islands around Taiwan. And we have also outrigger in Hawaii. So the baseline, the maximum baseline we can have is actually close to 80,000 kilometers. It's very low. However, the outrigger in Hawaii will have relatively small overlap in sky with Taiwan, because their sky and our sky is about 90-degree different. So in terms of observing overlap is limited. Therefore, it's quite important for us to find more available or suitable locations in and around Taiwan for this localization to work more efficiently. And that I'll talk about in next talk. And when we say 256 antenna, each antenna is something like this. It's a log periodic dipole antenna. I'll show later, but roughly it's about 1.5 meters in size. Something like this with an array. Okay. So the system design is quite straightforward. Each antenna is connected to some amplifier, and we can put in some filter to filter out the FM signal or the 4G mobile signal, and then signal is transmitted to the digitizer backend. And in our design, we have a FPGA based F engine, which does channelization, so forming, say, 1,000 channel out of this 400 megahertz band. And this FPGA F engine has a capability to process 16 antenna at the same time. So for our main array of 256 antennas, we only need 16 FPGA ports. And then the signal is transmitted to first level of server, which will process the signal, do the beamforming, etc. And then pass the integrated intensity beam to the second level server, which does the pulse search. And I'll talk about these parts in the third talk today. So again, this is image of some of the prototype antennas we have designed. So this one is in IA, this one is in the hotspot. Some of them are being tested on the site right now, but most other testing are done with commercial TV antennas, which is also very similar to this dipole antennas. So I'll show some beam pattern in the next slide. But the beam pattern is defined in two directions. One called the E-plane. E-plane is where defined with the dipole direction. And H-plane is perpendicular to this dipole direction. So you can see. So this is a beam directivity plot. So horizontal axis is direction away from the forward direction. And in the E-plane, the directivity is I think this one is a 3 dB beam width. So it's about factor of 2 lower than forward direction. And the size is about plus minus 30 degrees in the E plane. But in the H plane, the direction is much wider. So the size, 3 dB point is about, I think, roughly 45 degrees in each side. So at least 60 by 90 degree field of view for each antenna. So this is much larger than the area surveyed by China in this design. And also another thing to note is that why we need so many dipoles together. That's because combined we can form a almost frequency independent beam shape. So our beam doesn't change with the observing frequency. Right. So this is mostly for your reference later when we come back to this talk. So this is a basic functional block diagram of the F engine. So the FPGA will have 16 inputs. So you can imagine 16 duplication of the same thing. And there is a ADC component. We'll do the Fourier transform inside. But we put a polyphase filter bank in between to define the channel shape more precisely. And then, importantly, originally the data is sampled at 16 bits, so it's very high resolution. But in our case, we don't need all that fine digitization. So we only take the top 4 bits out of these 16 bits. So there's a requantization step to reduce the data rate, and eventually the data is packetized and transmitted through a 100 gigabit Ethernet interface to the computer. And so the design for an array 256 antenna is that we plan to connect a row of antenna from 16 antennas to one FPGA, and then for 16 rows we'll use connect to 16 FPGAs. The reason that we choose this is because then we can separate the beamforming in a 2-dimension separately. Hopefully we can absorb one of them, perform one of them inside the FPGA, and reduce the computing requirement in the computer. So when I say beamform, when I say how combine the signal from antennas to form beams, what exactly did I mean? It's basically a discrete Fourier transform. So you have n antennas, and you can form some n beams, and each beam each antenna is multiplied with this base coefficient. The beam size formed will be roughly lambda over L. L is the number of antenna times its separation. In our case, the separation must be greater than wavelength. And for the low frequency in our design, the wavelength is roughly 1 meter. So our design is about separation between antennas is 1 to 2 meters. So the array will be roughly 32 by 32 meters in size. In China, because the number of antennas involved is about 256. So to do this Fourier transform more efficiently, they employ fast Fourier transform algorithm. But in our case, we only do 16. So we think that doing a discrete Fourier transform, direct multiplication of the coefficient is probably equally efficient. And we have some flexibility there because we want to add other operation like RFI removal in it. So we'll talk about it later. So the operation then becomes, for each beam we have, for a particular beam K, we have 16 coefficient multiplied to the 16 antenna. And there are total of 16 beams. So there is an array of 16 by 16 complex coefficients to be multiplied to the 16 inputs time stream. But this is done for each individual spectral channel independently. So this is still quite a challenging task for the computer or for FPGA. But these beams, if we do the DFT directly, the beams will not be aligned for the different frequencies. So because the location of the beam, the antennas is fixed. So for different frequency, the FFT beams, there are, for example, in the 400 megahertz and 800 megahertz, the beam separation will differ by a factor of 2. So if you try to combine all these different frequencies together, they will not correspond to the same direction in the sky. It's not good. So in trying, they have to do a special step to align these beams together. This is what they call clamping. In our case, we can relax on the DFT requirements. So we just design 16 position on the sky and calculate the corresponding coefficient to those antennas, and we can compute these 16 beams at the same position in one step. Okay, so this is the plan. This is originally this plan is just requantization, but once we putting this complex matrix multiplication process, and the 16 antenna input after this process will become 16 beams output, and then but the data rate is still the same. And we'll go to the computers for the next step. Okay, so right, and when the data comes into the computer, we need to do the de-dispersion, like what ASIAA just mentioned. We need to correct for the delay and align the signal so that we can easily identify and integrate the signal along the frequency direction. So in this example, if the data comes from a nearby source, like quite close up, the dispersion measure is only 56 parsec divided by centimeter cube. The delay between lowest frequency and highest frequency is only 1.1 second in this case. And this is one example of the pulse de-dispersed from the correct pulsar. This is so-called incoherent de-dispersion. This is a very fast to compute. We just find out the delay for each spectral channel and then ship them back. This is called incoherent dispersion. But the performance is sort of not optimal. You can see that there are still signal is still dispersed at a lower frequency. If we could do coherent dispersion, then the signal from the same data set, you can actually improve the SN ratio by a lot. Problem is this step is very resource demanding for a computer.
Yeah, sorry, I have a question. So is this a kind of simulation, or you actually use the first prototype antenna?
No, not first prototype. This is data from Algonquin. So from not our data, but yeah, just demonstrating the difference between coherent and incoherent dispersion.
I see. Thank you.
So the most efficient way for post search still the incoherent dispersion. So that's the reality. This remains a key problem in maybe in the next decade. People will come up with when using new hardware, and maybe there are ways to improve this kind of efficiency. And you can do incoherent post search and improve the SN ratio a lot.
So that's one question. So for BURST project, you use just incoherent.
I think still mostly incoherent.
Oh.
There are very efficient algorithms written, but those are incoherent. You mean real-time processing? It's yeah, we have to do that.
Oh.
But when we trigger the event and we save the raw data, we can post-process those raw data using incoherent dispersion. So when we publish, the data will be, we can use the best processing we can do, but we cannot improve the SN ratio before the detection.
Oh, okay.
So we still lose some events.
So once we save the raw data, so actually we can go back to the coherent analysis.
Yes, that's right.
Oh.
Right. So outriggers, our plan is to have 64 antennas in each. So we'll cross-correlate the signal from outrigger to the main station. So the main station will provide the sensitivity, while outrigger will provide the angular scale information. So the resolution, say for 0.5 meter wavelengths for a station that's about 100 kilometers away, gives us 1 arcsecond resolution. So this is an important scale because for extragalactic galaxies, it's typically a few arcseconds in size. So if we can localize the source to 1 arcsecond, it's already a very precise localization target. So we know which host galaxy it comes from. And if we have 1,000 kilometer baseline, then we can localize to about 0.1 arcsecond. Then you can really say from which environment inside the galaxy the FRB comes from. Okay. And as I said, each outrigger station is continuously putting data into a ring buffer for about 30 seconds to 1 minute. And the main array will do the real-time processing and do the triggering. And when the main array detected a source, it will trigger the outrigger stations to save the buffer in the past 1 minute or so to a disk. Then you can use saved data for post-processing VLBI analysis. And so far, I haven't talked about polarization, but our main array will have single polarization because if we try to do 2 polarization in 1 antenna, it adds additional loss, so sort of affected the sensitivity. So in our aperture array design, because we don't have any reflector, we can actually separate the two polarization in two different arrays. That doesn't increase any complexity or difficulty in analysis, but it's a more sensitive way to do the telescope. But for our purpose, we'll use a single polarization for main array, or just to detect the source. And at least two other outriggers will have the same polarization, same linear polarization. So it solves the Stokes' I and also the location, localization of the source. And at least one other outrigger can have a perpendicular polarization to help us detect the rotation measure, etc. So we'll depend on how many sites we can use or how large each area is. So there are still some uncertainty there about the design, but that's outline what we want to do. Okay. And in fact, one of these perpendicular polarization can have the same location as the other parallel polarization array as well. So the same, one of the outrigger site, if it's big enough, you can accommodate one parallel polarization and another array with a perpendicular polarization. Okay. So even with only 256 antennas, because of our large field of view, large survey area, we can have better cadence of observing. So we don't have so much empty time on any of the targets. So it's easier to spot bright and rare targets, maybe close to us, and maybe probably more nearby. And this means that these hosts will have a much larger angular size because they are nearby. So they are very good for follow up the detailed environment of each target or this FRB compound. And at the current sensitivity, we estimate that let's start here. When we finish, we can have roughly one FRB per day or per several days, and it's already very competitive to other planned telescope. And if we increase to the next phase, say 2,000 antennas, then we can detect maybe 10 FRBs every day. So that's a lot of candidates to be had in the near future. Okay, so yeah, it's about the first introduction. So we have just started a lot of things in the institute, and we'll need to characterize the system and site, and realize these are beamforming, and do some antenna calibration, and try to remove RFI, and also work on the real-time processing, and also work on all these other things in this project. So there are plenty of work for people to join and to contribute. And in next talk, I'll talk about this, the blue one, the site characterization and RFI removal. In the third talk, I'll introduce real-time processing as needed there. And so I think I'll stop here. So any questions? Sir, okay, please go ahead.
Can you explain again how its work is about the E and H? I forget how to code it.
Yeah, E plane and H plane.
Yeah, and how does it work?
How does it work? Let's see.
Yeah.
Right. So because each dipole is resonating with the incoming signal in one direction. So in this spatial direction, it has a better directivity. Means for the signal coming off too much, it will not resonate very well. So in the E plane, you can only see smaller field of view. But in the H plane, actually signal coming from different direction doesn't affect the resonance very much. Therefore, the field of view is much wider.
Oh, so the tiny metal
These ones.
to detect the resonance.
Yes, these are dipoles that to detect the incoming signal.
Oh, okay, thanks. By the way, something obstructs my vision in front of camera.
Oh,
Okay.
sorry.
Somebody move it.
I think this one.
Oh, thanks.
Okay. Thank you. Sorry, question?
Okay, so I have two questions. So first is for the VLBI,
Yes.
we have sort of east-west baseline from Hawaii and Taiwan.
Right.
So I'm not sure if it's enough to just localize anywhere because we were lacking north and south baseline. I don't know if it's a problem or not.
Yeah. Okay. So that's a good point. So yes, there are two directions that we need to localize. So in the next talk, I'll show the potential sites we have surveyed. So hopefully that will be more evenly distributed in north and south and east and west, but not 8,000 kilometers, maybe a few hundred kilometers.
Okay. So the second question is, could you remind me how you handle those heavy data flow? Because I believe it's an 800 gigabyte per second. I'm just curious about how you handle that.
Okay, so in our case, I think I'll talk more about it in the third talk, so real-time processing part. So basically, it relies on fast network interface and also clever way to work with CPU and memory to actually achieve this kind of demand. Otherwise, you have to do a lot of parallelization,
Yes.
like in China, because this hardware in 10 years ago less powerful, so they actually have to distribute work to many more servers, and we hope we can do it with less server.
So after like processing to beamforming, will the data size be decrease a lot? Or?
After beamforming, actually the data set is still comparable. I mean, this is all basic linear operation. We didn't add or we didn't reduce any information. But after beamforming, we'll do some bandpass calibration, and once we are satisfied with that step, then we'll make an intensity beam. In that case, in that step, we remove the phase information altogether. And once we remove the phase information, then we'll do the integration. And that part, we plan to integrate down to about 1 millisecond time resolution. So that in that step, we'll reduce roughly a factor of 100, 200 data rate. And for post search, it's much manageable.
Thank you.
Sorry, I have a related question. Sorry, I just want to make sure. So 800 gigabytes per second. I thought it was about the chime, but actually it is burst
800 gigabyte is chime.
chime. So
Yeah.
do you have more data than that, or?
We only have 256 receivers.
Yeah.
Not they actually have two polarization and 4 times. They have 2K receiver, so we have less.
Actually, yes.
Yeah. So our case is about 100 gigabyte per second.
Oh, okay. That's interesting. And also, I have another question. In the end, you show the many components here. And then I just wonder if you are organizing all of these things, or so. I mean, my question is, say, China already did a similar thing already,
Yeah.
and they have their own experience. Therefore,
Yeah.
which part is, say, easy to do using the China experience, and then which part we have to do from scratch or first? So.
Yeah, so I think the pulse search in real-time processing part is something we actually already have. We can already use their software. So this part is more or less done.
Okay.
For our initial testing. Integrating with something, everything else still requires some work. But all the other things is kind of different for each project. Something extending.
So we need to do by ourselves.
Yeah.
So which part is the most difficult?
Which part is most difficult?
Which part do you need more power?
Maybe we can talk about this after all 3 talks. We have some time for discussion.
Okay.
Okay.
Maybe this is a stupid question, but I wonder, because the burst is optimizing for FRB detection or maybe pulse detection, so but still maybe we can do some science with the archival data, maybe much later than the original survey project. So do you have any plan to kind of save the raw data? How much raw data you will save for the future or to the community?
That's an interesting question. I haven't really thought about it. But in principle, we can save some kind of raw data, but not some kind of process data, but not raw data. Whether there's a FRB or not, just some kind of integrated information. But yeah, we don't have anyone working on it right now.
Of course.
So
Just curious.
yeah, that's an interesting idea. And
Maybe
in Chime's case, they have 3 separate backend correlator backend to do different science. So one backend dedicated to cosmology integration kind of analysis, and one backend for FRB, and another higher time resolution one for pulsar science. So yeah, so depend on so something we have to think about whether existing hardware can do it or whether there's something we need to add.
Thank you.
Interesting question. Okay, so there's no other question, then maybe we can go downstairs and take a look at the actual hardware, and we'll come back to another talk to 30. 16 antenna in this one board. Okay, so we have 1 here and 3 more here. So currently we are testing whether we can actually feed all 4 FPGA into one computer. I think there's a testing board here to put some filter in front of for the incoming signal, and then it's feeding to the input port. Yeah, the filter inside here. But this one is for testing only, so it has for different inputs, it's for different frequency range. we'll start the next session. In this talk, I'll talk about some site testing with the prototype system we saw in the 11th floor. We call it the bladeRF device. So this is just a recap. So our system will have a main array and some outrigger arrays. And for 100 kilometer, we think we can achieve roughly arc-second level spatial localization resolution. And originally, we have some testing site in Hawaii. So it's meant for correlation as an outrigger station with China. And between Hawaii and West Coast, Canada, there's only 3-hour difference, so 45 degrees in sky. But between Hawaii and Taiwan, there's a 6-hour difference, or 18 hours the other way. So our sky is offset by 90 degrees. That means even if we try to angle our antennas toward each other, we are still not very well aligned. I mean, will be covered by the ground. So we want to find some more stations in Taiwan or around Taiwan to build the outriggers to correlate with the main array. So this is the original one. And this is the current status of the sites that we have negotiated and also been to do some kind of testing. So the main one that we probably will put the main station is the Fusan Botanical Garden. So it's run by the Forestry Research Institute. So they actually welcome people doing research to use their site. But it's a protective area. So when we construct our station, there are some restrictions there. So it's kind of difficult to work on. But I mean, in terms of management, they are welcoming us to do the research there. We did some initial survey there, and we found that in some secluded location inside the garden, the RFI looks very well. So that's one main site. And it's not very far from Taipei. It takes a few hours for us to get there. So 1 to 2 hours from Taipei to that site. So it's relatively easy to access. So we have another site in Nantou, which is about 140 kilometers from the Fusan site. And that site is managed by NTU experimental forests. So the condition there is also quite nice. And they have a building for us to use, etc. So for the initial testing, it's a very good site. And one other testing is in Cape Fugui, and this one is managed by Academia Sinica, another institute, the environmental change. I forgot the exact name. So so that site is also very accessible, only about 1.5 hours from Taipei. Problem is there is an Air Force radar station just nearby, like 20 or 50 meters away. But that radar is emitting probably at a few gigahertz, so not in our frequency. But I think the background there is still a bit higher than Nantou and other places. So that's probably something for us to test the outdoor environment for our equipment, but not for long term. And we have also done some initial surveys in other sites in southern part of Taiwan, but we haven't put the the prototype system for testing yet. And another site that we have tested is Green Island. It's about 230 kilometers south of Fusan. So this will practically be the north-south longest baseline in the initial phase. And the condition here is also very good. There is also a longer baseline in Dongsha, 650 kilometers, managed by originally by Zhongshan University, but now it's being transferred to Ocean Council. So another higher level office. So we haven't negotiated with them yet, but we'll see whether it's possible. But it's not so accessible to us right now. And we also talk with people from Ocean University, who has a campus in Mazhu, Beigan. It's also about 200 kilometers from Fusan, but in the more western and north side. So it's also a nice baseline. So later on we may go there for testing. And besides the sites in and around Taiwan, we also talk with Japanese radio astronomers and people from NLJ. They are also interested in our project. So they say they'll welcome us to do a VLBI later. So when we are more or less ready, we can negotiate with them with about the data format, etc. Then we'll talk about future collaboration there. So all this will be will more or less share almost the same sky, and at least in Taiwan, we should be able to reach roughly 1 arcsecond or better resolution. And if we include Ogasawara Island, then it's much better. Yeah. So we have some good prospect in the sites. So how do we determine if a site is good? So the first method is by using a spectrum analyzer. So we just connect the antenna to some amplifiers and then to the spectrum analyzer. So for a single antenna, we will be able to see the radio signature in each site. So we'll be able to see the background level and how strong each emission is above this background level. In this case, there are some bands here. This is correspond to the TV stations. And each TV station is about 6 megahertz wide and separated by 6 megahertz and another station. And then this is around 500 to 600 megahertz. Then above 700 megahertz or so, there's a 4G mobile signal. These are the strongest signature in every site. Okay. And then there are other radio bands being used by other like radar or some other stations out there. Yeah. So in every site so our goal is to find some shielded place, like in a valley. So when we look at the sky, it's not blocked, but it hopefully blocks most of the interference from other directions. Okay, so Fusan Botanical Garden is good. And in Green Island, it's not a valley, but it's there's less population in nearby, so it's also a good place. Okay. So it's easy to set up for a single antenna spectrum analyzer method. So we can screen out bad sites really quickly. And so we can also see the RFI strengths roughly. But it doesn't tell us much more than that. And the second method is the setup that you see out on the 11th floor. We use a small device to take some digitized signal, and then we can put multiple antennas and do cross correlation to learn more about the site. And in this case, this is one test we do in Fusan when we use some batteries to power the entire setup for one night of testing. And in other sites where we have power, then we don't need to use a battery system. It's much more stable. But in Fusan, we are still working on pulling the power to the testing sites. So it's still taking time.
I have a question.
Yes.
Maybe I have maybe already asked about this one, but when you take up data, so you spend maybe one day. So for example, my question is the daily variation.
Yeah.
Day-to-day variation.
Right.
How large is the day-to-day
Okay.
variation?
Let me show this one. Maybe in the next few slides, maybe. So let's see. So the device is made by a company. So the product name is bladeRF. It's a software-defined radio, so SDR. So if you search SDR device, there are many companies making product like this. But this one is offer one of the widest bandwidths available out there. So it's a kind of a new product. So it has a variable, I mean, you can tune the radio frequency from roughly 50 megahertz all the way to 60 gigahertz. Anywhere you can tune it with up to 40 megahertz bandwidth. So it actually supports 2 receiving channels and 2 transmitting channels. So you can actually program it to do some synchronization. For example, you can emit some signal and let the other antennas receive it. So there are some things we can play with here. So in each sample, the ADC here will sample the data in 12 bit. So this is not as wide as the FPGA system downstairs, but it's enough because we eventually only want some a few bits. Yeah. But this step is still important because later on we'll talk about the RFI removal. In that case, enough resolution is still needed. And it's a complex sample, meaning that you sample the real part and imaginary part of the incoming signal directly. There is actually a FPGA on this device as well, but by default we are not using this FPGA. So all the digitized signal pass through the FPGA and come to the USB interface and go to the computer. But yeah, because we are not trying to do the real-time processing with this device, we're just trying to capture raw data and to experiment with the data analysis steps. Okay, this for your reference, this is the functional block diagram of this particular device. So if you need it later, you can check for details. So to use this device, there are many software out there that can do the SDR analysis. For example, one popular choice is GNU Radio software package. So it also supports the bladeRF device. So in this case, you can GNU Radio offers some blocks you can lay out, and then lay all the function you like, and then generate, for example, a power spectrum for each channel from this device. So it's really easy for us to begin the development and to easily see whether everything works or not. However, this GNU Radio is using Python, and the data it's outputs it takes is converted to complex 64. So this is actually more than what we have from the data. And they're also producing some kind of bottleneck for the USB to CPU bandwidth. So when we use the maximum bandwidth, there are some problems, and we have some unexpected data dropout. So eventually, we have to discard the GNU radio and use a different approach. And this bladeRF also comes with a scriptable command line interface called bladeRF CLI. So using this interface, we can record the raw data without losing any data normally. But there are still some data loss. So we are able to know when we lost data, but it's not too significant a problem yet. And originally, this software does not provide timestamp in the data. So there are some metadata information that we should be able to obtain from this device, but it's not enabled by default. So we have to modify the source code in some way to obtain this kind of information. So right now we're using this modified version. Unfortunately, in the process, we disable the transmission function. So some of the benefits we expect to have, like synchronizing the data with a TX function, was not available right now. So yeah, so hopefully someday we'll get to it and fix all the problem and be more flexible. Yeah. And also, the product also provides some other low-level C language API, so we can write our own program to control everything in a much more flexible way. But that's no one's working on it yet. So this is one example of the data from Fushan. So horizontal axis is the frequency in megahertz. I think I'm missing the label here. I think this is 200 megahertz. This is 800 megahertz. And the gray line indicate the terminated input. So I put a 300K termination in front of the LNA. So you can interpret the gray line as a 300K load in front of the antenna, in front of the LNA. So the sky is lower than this 300K, because normally sky shouldn't be emitting so much. And TV stations are visible. Different colors just means each data set can only observe 40 megahertz bandwidth. So they are indicated by changing color. Okay. So this is what we call Site 1 in Fushan. It's not the best site in Fushan. It's actually the worst site in Fushan, but it's easy to get there. We can just park our car next to the site and then do the experiment. And we have a much better site called Site 6 in Fushan, but that one needs some development. So we'll do hopefully do that in the next couple of months. Okay. Okay, this figure is better. So yeah, 200 megahertz all the way to 800 megahertz. So in this figure, the top gray line is the same one as before. That's the termination input. And there's a lower gray line here indicating that also termination input, but LNA is being turned off. So this is telling us the backend noise, the absolute minimum floor we expect. So things should always be above this line, this gray line. So we're detecting something other than the backend. And in Cap Fugui, the background is higher, so you can see that it's
almost 300K in most cases, and some of them higher. And the color here, you can see transparent one and a solid one. And the transparent one means the, I think this is a 24-hour variation, the minimum to maximum range. And the solid color is 15% to 85 percentile range. So roughly 1 sigma range. The transparent one is the minimum to maximum variation. So in Fugui station, the variation is actually quite significant. And we found that this variation is time dependent. It's mostly between, say, 6 to 9 p.m. to next day. Yeah. So mostly in the night it's stronger, and daytime is a bit weaker. So it's not as strong in other sites. Okay, this is Nantou. We call it Longtian campus. So this one. So this one, as you can see, the background is much better than the Fugui station. And variation is also much weaker. Yeah. So except maybe this band is not so good, higher variation. Yeah. So Dongsha, as I said, we put 2 antennas in Dongsha with the help from the research assistant. We're able to take in some data. So again, the background is quite low, below the termination input, and also not much variation in some of the band. And the TV station is actually quite weak. And we'll talk about how to reduce those known RFI, fixed location RFI later. So this is a very good state, especially this 4G band. It's almost empty. So very, very good site, except that it's hard to access. So we'll probably, when everything is more or less ready, then we'll put our equipment there later. Another thing in Green Island. So again, very good site, low variation. But this one is also only for 8 hours, I think, this plot. So we'll do some update later. So we have some very good sites around Taiwan ongoing. And from this site, these observations will try to characterize the system noise using observation of the sun. So we use some available database which tell us the solar flux between at some fixed frequency. The most relevant one is 400 and 600 megahertz. And in most cases, it's pretty stable. So it's roughly about 0.5 million Jansky at our interested frequency range. And from our data, we can look at the SN ratio of the solar signal to the noise. And we estimate a few million Jansky up to 10 million Jansky from our data. So we can compare to our expectation. For example, our LNA has a noise figure of about 35 Kelvin. The state-of-the-art LNA is probably even better than this. This is a commercial one. And the best one is probably even 20K in first LNA. So we expect that the whole system noise is probably, we can achieve maybe as good as 50K. But in the worst case, if we have other insertion loss or something mismatch between antenna, etc., then we'll probably increase the system temperature to 150K. And assuming 150K and some antenna effective area, we can get a rough estimate of the expected ICFD, which is around 2 million Jansky. And so for Green Island side, it's actually pretty close to this number. But at some higher frequency, the SCFD was worse. So this is something that when you come here to work on the data, this will be something everyone can work on for different site, different antenna, and to analyze this kind of system characteristic. So the data originally looks something like this. So let's look at the left-hand side first. So this will be the autocorrelation from two antennas. So the power from the two antennas. And this is a cross correlation between these two antennas in amplitude and in phase. So you can see some strong interference that's almost has the same phase over time. But other than these interference, in between the bands, you can see that the phase is changing with time. And this changing with time is because sun is moving across the antennas. So the phase is changing. And we can subtract off this static signal. And after subtraction, most of the interference is gone. So you have a clean observation of the phase of the sun. And so this is a measurement of the phase as a function of time. And the orange one is the expected phase of the sun. So I didn't subtract off the offset from the measurement, didn't calibrate it, but mostly the fringe rate is in perfect agreement with the observation. And we have observation from other frequency. And at 500 frequency, 500 megahertz, the agreement is also pretty well. But in some frequency, we have a strong interference that's not static in time. It's also changing in time. So it's not easy to subtract off in a simple analysis. So therefore, this band will not be usable in this analysis. But in the in the band outside of this interference, we can still detect the phase change as a function of offset of the sun. So without subtracting off the data, we cannot measure the sun fringe. But after removing that removing the static signal and looking at some part of the data, we can already sort of see the variation, the sun fringe. So, but it's still much more noisy than the other frequency. So the SN ratio here is not very good. And for other frequency, yeah, so also not so good. Okay. And 700 megahertz, we basically fail to see a clean signal of the sun. Okay, that's one way to look at the data. And another way is to define the cross-correlation coefficient. The cross-correlation coefficient is basically normalizing the cross-correlation of two antennas by the autocorrelation. Okay, so at each sample, this cross-correlation coefficient has a maximum of 1 and minimum of -1. But it has a random, some phase. Phase information is preserved, but amplitude is normalized to 1. And if everything is perfectly correlated, then you get a correlation coefficient integrate to amplitude of 1. and it's smaller, then you can sort of interpret it as a SN ratio, or signal divided by the system noise. But of course, we are assuming that the autocorrelation is dominated by thermal noise, so that thermal noise is represented by the SEFD. But if it's dominated by the RFI, then this approximation fails. But that's one easy way to look at the system performance. So again, come back to one of the data set, 460 megahertz. So I just put a cross correlation here. And this is again a phase as a function of different time measurement. And cross correlation, if we plot the correlation coefficient as a function of time, we can see that it's, well, number is small, but roughly it's about 0.15 to 0.2. So 1/6 or 1/5 of the signal is about factor 6 or factor 5 lower than the SEFD. Okay, so
when you say cross correlation, so correlation between what?
two antenna signal.
Two antennas. Are you put the two antennas in the same site? And then take a correlation.
Yeah,
Oh,
yeah.
okay.
This is basically the same data from previous slides, just emphasizing on the amplitude of this cross correlation coefficient.
Oh.
So we can take this as a SN ratio measurement. And in this frequency at Green Island site, this is about 0.2. So since the sun is about 0.5 megahertz, megajansky in flux, so the system noise here is about 2 megajansky. And it's quite consistent with the quick, simple estimation. So it means that the system temperature is roughly 150 K. Okay. And at 500 megahertz, the SN ratio drops to, this is about 0.1 to 0.15 or so. And in Fugui, Cap Fugui is much more noisier. So the SN ratio is roughly 0.1. Okay. Okay. So we can use this to characterize the system performance at different sites. But all these are using the same TV antenna right now, and we will deploy more different type of antenna to the sites for testing later. Yeah.
So basically the difference is coming from the different environment.
Yeah, different environment, right?
Oh,
yeah.
Antenna should be the same.
Right. And LNA right now the same too. Yeah. Okay. And another thing we can do with this kind of data set is that we can try to filter out the RFI. The idea is called spatial filtering technique. For this to work, we have to have multiple antennas larger than 3, I think. Probably 4 or more is better. So far we have tested this method with 4 antennas, but we probably can do more. With more antenna, we should be able to get better performance. And the steps of this, the idea of this spatial filtering technique is that you form a covariance matrix between the 4 antennas in this case example. So there will be cross correlation, 16 cross correlations. I mean, some of them redundant, but they after averaging over time, they tell you the phase information between these 4 antennas, and we can do eigenvalue analysis of this covariance matrix to find out what combination between these 4 antennas in terms of phase information contribute to the most variance of this covariance matrix. And that combination between the antenna is essentially, you can think of it as a direction information from the source, the dominating source. Okay, so with 4 antenna, you can you can decompose the covariance matrix into 4 components. So if you only have 1 or 2 dominating RFI at each frequency, then once you use this decomposition and you can remove those 2 dominating components from your data, then you can reduce the RFI interference by a lot. That's the basic idea. So with 4 antennas, you cannot remove more than 3 components. The more you remove, the less information you have left, and the SN ratio will also degrade a lot. So far we tried removing 1 or 2 components, but if we want to do, if the environment is too complicated, that for example, your dominating signal, say, have a direct path to your antenna, but also reflection, for example, then you probably need to remove 2 components. And if you have multiple reflection, you probably need to remove more at each frequency. So it can be quite complicated to analyze, but we're trying to see whether it works in a simple case. Okay, so in this case, this is data from one of the Taroga experiment site. We just, in the early phase, we borrow their site and their antenna. We put our testing equipment at the end of their data chain, and then recorded some data, and then trying to see if we can analyze the data this way. And this is some data at 275 megahertz. And we can decompose the data into the 4 components. There are strong eigenvalues, and then median ones, and weak ones. And if we remove the strongest component of the RFI, our data will be, we can remove a lot of the, probably 20 dB of the RFI signal, almost 30 dB removed. But that means the RFI from that side is almost a single point source. So it's easy to remove. Only 1 component can achieve this kind of reduction. In another case, in Fusan, when we have 3 TV stations in this band. And in this case, the orange one is the original data. And in the green one is removing one of the component, the strongest component. So in one station, one band, we can remove roughly 20 dB of RFI from this band. But this same process applied to different frequency band is not so good. And that's probably because different stations, they originate from different TV tower. And some tower has a single line of sight. Some tower maybe originally they split the signal into 2 different towers to boost the signal. So there are multiple sources, or there are some multiple reflections. So removing a single component does not remove the RFI so well in different frequency. But if we try to remove 2 components, then maybe we got 20 dB suppression in this band as well. But of course, then the SN ratio will suffer, so it becomes noisier. Yeah. So.
I have a question.
Yes.
So in this subtraction process, actually you are just removing the stable outline only.
Yeah, right.
Therefore, you don't remove FRB from this process.
Ideally, no. Yeah. So when we construct this covariance matrix, it takes some integration time. So hopefully FRB or any phase varying signal will be diluted. Yeah. So we only remove the strong RFI in the site. Yeah. Yeah. But if the RFI is a moving source, like a boat or something, yeah, then maybe this won't work. Yeah. So there are some limitation. Yeah. And let's see. So the idea for this kind of removal is that we'll do some this covariance matrix is if we have 16 antenna in the final system for one FPGA, then this covariance matrix is a 16 by 16 complex number matrix. And we do the projection onto eigenvector, nulling, and project back to the data space. This combined is also 16 by 16 complex number matrix. You can apply this combined matrix to the data. So this whole step is reduced to a 16 by 16 matrix multiplied to the 16 input time stream. And this is exactly the same operation that's needed for the beamforming. It's also a DFT or 16 by 16 complex matrix multiplied to a time stream. So we can combine these two. So we can do these two steps with one computation. We just need to pre-compute this matrix and then apply it to the beamforming matrix. So we can do this without additional computation cost. That's the beauty of this thing. So even if it's not perfect, the RFI suppression is not perfect, we don't actually lose anything. Yeah. So
this procedure has to be applied to different sites. We have many sites.
Right.
So we apply this method independently.
Yeah, independently. That's right. So we have to compute this matrix characterize each site, yeah, separately. But in order to compute this matrix, you have to get the antenna data out first, then do the computation and feed it back. Yeah, so we probably need a different pipeline compared to the real-time processing pipeline. Yeah, I'll probably come back to this later. Okay, so just a summary. So about the things that needs to be done for this offline analysis or site testing. So basically, mainly for people in this room, I'd like to encourage you to join us, and then we can always start with the characterization of the site. There are still many things to do. We'll try different antennas, test different sites, and also we like to understand the variation as a function of time and frequency, etc. And we'll continue to experiment with RFI removal technique with more and more antennas and see how well we can implement this technique. And with more antennas, we can also play with beamforming technique. We can, for example, form several beams and then observe the sound passing through different beams and the signal from each beam, how it changes, whether it's as we expected. And or we can initially form a tracking beam that should always track the sound across. Yeah, something to build up our confidence. And later on, because VLBI in its in nature is offline processing, so this is also something we can play with to verify that we can actually form VLBI from multiple stations with a known source. Yeah. So, and that requires accurate timing and etc. Or the GPS testing we saw out there. So all these are still under investigation and needs some effort. Yeah. Okay. I think I'll stop here. I'll take questions.
I have a question. So now we have many candidates for science.
Yeah.
And then how do we decide? So actually we are current state is, so we are collecting data for decision. And then later we will judge if we really want to put antenna in this location or
Right.
we give up this place or something.
Right.
Or we try to put all the places.
Right. So as you our rigor station, we need at least 2 or 3 sites. So actually, we don't have much more than that right now. So almost everyone is needed. But besides the Fugui station, probably Nantou, Green Island, maybe Dongsha or Beigan.
So basically, we plan to put antennas there. Or
Yeah, yeah. But there are still some other sites in southern Taiwan we haven't tested yet. But if Green Island works, then the southern Taiwan probably doesn't offer too much improvement. Maybe it would be decided by accessibility. But Green Island has an advantage that it's quite clean. Southern Taiwan probably not so clean. But in between Taidong and Pingdong on eastern side, maybe there are good sites. But that's also difficult to access. I mean, equally difficult to Green Island probably. Yeah.
So in that sense, if students can contribute some components here,
Mm.
and then that will be used for the real observations
Yeah.
in the future.
Yeah,
So,
that's right.
okay.
Yeah. So not just for exercise. This is
just
real
Yeah.
effort, real contribution.
Okay.
Yeah. Yeah. Yes.
So I have a question on this. So, like my students, most of them here are like master first year.
Let's begin the last talk, last presentation today. So this part is I'll introduce some of the ideas for or problems we need to face in the real-time processing. This is also something we just begin to investigate. So not much data to show here, but to introduce you some of the questions we need to solve. And this is coming from the effort from Andrew, Xiuxian, Zhiyi, and Xianqun. Okay. So another schematic diagram of the so-called structure of the data flow. So the antennas here have each row has 16 antennas and 16 rows of them, and into 16 FPGA, and then
There are no cells.
sorry.
No sound.
No cells. Hello?
Hello, sorry, I muted myself. Sorry about that.
Okay, thanks.
Okay, so just showing the another schematic of the data flow for the project for the backend. So we'll have 16 FPGAs taking 16 row of antennas. Each row is 16 antennas as well. So for each FPGA, we have 6.4 gigabyte per second of data into a big switch. And then the data will be received by 4 servers. Each server will take a quarter of the data. In this case, because originally there are 16 antennas as input, but after beamform there will be 16 beams output. But we need to do a second beamform here, combining the first beamform is say in this direction, and the second beamform is in this direction. So we'll take 1 beam from each FPGA to form the second beamform. So the server will take a quarter of the data, meaning 4 beams from each FPGA, and combining all 16 FPGAs to form the second direction of the beamform. So output is 4 times 16. There's 64 beams from each server for 1,000 channels. But in the input data, it's a 4-bit sample after some bit reduction. But in the CPU, CPU does not support 4-bit operation. Also, when we do beamform, we have to do a lot of multiplication and summation. So we should increase the bit depth to 16 plus 16 bits. So the data rate is a little bit increased. But after the beamforming and some calibration, we'll do the intensity beam and some integration. So the data rate will reduce a lot. So in the end, all 256 beams will transfer to the same processing server here for post search and signal triggering. Okay, so I'll focus on these 3 parts in the next slide. Okay, so about data transfer between the FPGA and the servers. So currently we are putting 2 dual port network cards in 1 server. So we plan to receive 4 FPGA cards to the 1 server, but whether it can actually achieve this kind of data rate without loss of data is something we are still investigating. So theoretically, each channel of each network card should have a bandwidth of 30 gigabyte. So it should be sufficient for 2 FPGA board, each with 6.4 gigabyte. So theoretically, it's doable. So it's something we are still trying. So the problem with implementation of this kind of work is that the CPU loading, maybe if you need the CPU to care about what's inside the packet before saving them to their destination, and it takes a lot of time, a resource. So we want to reduce that kind of loading, and we also want to increase the data so passing the data directly into the cache for CPU to access. So there are some technical details of how to implement this. And we're trying to use some new technology, which usually most people don't need to care about. But for this kind of high data rate processing, these are all important details. So this is something we are trying to develop our own experience. And for example, in China, they use a framework called Data Plan Development Kit, or DPDK. So in this case, the network card does not pass the data to kernel. So kernel does not know anything about what's inside the packet, but it directly pass the data to user space memory or to CPU. So that can reduce the latency from the system. But that's kind of something you need to spend some time to familiarize with. Okay, so still ongoing. And about the beamforming, as I said, we need to convert the data from 4-bit to 16-bit. But even 16-bit data computation is not a common operation in CPU. Mostly the standard computation is 32-bit floating point. So trying to find the right CPU instructions that can accelerate this kind of computation is the key in this beamform or this complex multiplication task. So our colleague is using the assembly language to utilize CPU functions to actually make this happen. And so far, our initial test shows that because from each FPGA, every second we have 6.4 gigabyte of data. And if we use a single core, it takes about 30 seconds to perform this kind of beamform operation. So this is not real time at all. So we need to parallelize this kind of operation. But even for only one beam, we maybe need 30 cores. But we're trying to use the next generation of CPU, which has optimized instructions for our application. And unfortunately, the 4th generation CPU originally was announced to be available this year, or probably last year, but it's delayed several times. So the latest news is that we may be able to get this CPU in later this year or early next year. So supposedly this will accelerate the process a lot, but also something that still under development. So anyway, so this is just a kind of an advertisement for people who are interested in this kind of computer information science kind of technology, and this is something new and something will be interested by other projects as well. Yeah. And for post search, we've introduced this before. So in this example, this is multiple posts from the pulsar. So if you look at this data, you can actually see regular posts, right? And there are also interposts you can see. I mean, the main post and some interposts. So we want to do the de-dispersion, and in this case, this is again from crab post, I think. So the 56 DM. In this case, it's de-dispersed as shown here. But let's see. Yeah. So our goal is to find FRB with unknown DM. So we have to define a range of DM parameter that we want to search. So from the experience of Chime, we know that at least almost probably 90% of the FRB have DM less than 1,000. Okay, so our initial goal is to search for DM range between 0 and 1,000. And for that, the maximum delay is roughly 20 seconds between 400 and 800 megahertz. And if we go to lower frequency, I think the delay will be slightly longer. But that will be the spec. So something like 20 seconds. And we like to process those in real time. And this example is from Bonsai. This is a package used by Chime to efficiently search for the FRB or for pulses with unknown DM. And it's, I think this version uses only CPU, but it's already quite fast. And the idea is still essentially incoherent dispersion. But it converts the data from frequency and time to the DM and time space very efficiently. So the algorithm. So they, after conversion, so you can, for each pulse, you can see the maximum DM, most likely DM in each pulse. And since it's a single pulsar, so it's all the same DM here. But if your data have different FRBs, then the DM can be somewhere else.
I have a question.
Yeah.
So yeah, I agree with that. It is reasonable that we limit the maximum dispersion measure up to 1,000. But this is say you mentioned this is initial goal. So therefore, do you plan to expand up to say 3,000 or something? I'm asking because recently, like very low FRBs which has very high dispersion measure, say about 1,000. Therefore, if we limit 1,000, it's still nearby, but some FRB may have very high dispersion measure. This is coming from the host galaxy component. Then we may lose that kind of FRBs. Therefore, in future, we may want to extend more higher dispersion measure if possible.
Right. So initially, I mean, right now, in our case, using Bonsai, if we search up to 1,000, for 20 seconds of data, it only takes about 2 seconds to process. So it's actually very efficient in this sense. So depending on we can actually use a more powerful computer in the back end. And it's possible to search for wider DM range, as I expect. So this is something we can upgrade later, I think. Yeah. So right now we expect that with only 25 cores, we can process 256 beams. Yeah, something like this. So as I said, this is already tested and already existed, something we can already use. So our work will be somewhere on the other part of the, yeah. Okay. And so I just want to put things that I mentioned before together here. So in terms of real-time processing, it's the 3 things that I mentioned earlier: the data reception, beamforming, and pulse search. But besides that, we'll need to update our gain table to optimize the 4 bits. Otherwise, if the gain is too high or too low, the 4 bits will not be optimized. So we need to update this gain table more frequently. And we also need to calculate these RFI removal coefficients semi-regularly, maybe daily or several hours. So all this, also we need to take care of the gain calibration from each antenna so that we can actually meaningfully combine the antenna data. So all this requires measurements of the antenna signal. So it's not covered in it's a branch parallel to the real-time processing, but the data will need to be feedback into the real-time processing pipeline. So all this will also need eventually someone to look into, to work on. So, and after the pulse search, we'll need to have a working mechanism to trigger the outriggers for saving the ring buffers, etc. So all these works needs to be done. And as I said before, we need to do VLBI. So the base mode of operation is that for each site we'll have a GPS time server. So it can synchronize the system time to maybe microsecond level. And it offers a reference clock from the GPS. So we can use it as an external reference for the FPGA. And we'll use the 1 pulse per second pulses from the GPS to initialize the FPGA data taking or the clock of each FPGA. But this is roughly microsecond level. So this is not probably not good enough for the final localization requirement. And we can probably improve that with calibration of radio sources on the sky. Or additionally, we have multiple GPS satellites on the sky that is visible through the multiple stations. So we can try to use a GPS carrier signal to do this time calibration. Yeah. So there are many references on this kind of research as well. So in principle, it can provide nanosecond accuracy for the timing. So that's something also we need to work on. Yeah. Okay. So yeah, so we're just at the beginning of this this part of the work. So there are still lots of work to be done, and also lots of things to learn right here. So okay, and then some of these should be tested with the offline analysis system. So our goal is for people here to familiarize yourself with offline analysis, and then gradually move on to the other advanced topic later, when depending on how you like to, or which topic you are more interested in. Yeah. Okay. So I think that's about it. Any questions so far? Yeah. I have to say this is yeah, as I said, this is a very initial early phase of the development in terms of real-time processing. Yeah. So still not much to show here, but
so I have very practical question.
Yeah, sure.
So in order to invite more students to this project, so in practice, students need to write a paper. For example, if he or she is a PhD student, they need to write a paper for graduation, or even for master students.
Yeah.
And then I just wonder, so we have many components here, right? And then say one master student may be in charge of this component. And then can we really write a paper using that component? Maybe instrumental paper will be fine, but if we can really provide something good topic that they can publish paper, that will be very good for their career, then it might be easier for them to jump in this project.
Yeah,
so therefore, I just wonder, how can we organize, or maybe if you have maybe we want to have a kind of list of components, then maybe we can publish this paper or this paper or something like that. If we have something like this, then it would be very good.
Yeah, yeah. That's I think we still need to talk about or discuss how to organize this way. Yeah, but that's something we should do. Yeah.
I know that for some big project, actually, say instrumental things, they can publish paper, right? So we construct this instrument. Stick ladder. So for instrumental papers, so for big project, say if they construct some certain instruments for observations, then they can make paper like that. I just wonder if we can do similar things from this project, then that would be very good for students.
Yeah. So so like for example, this kind of GPS carrier thing, it's there are some applications on other projects, but whether we can, I mean, other VLBI probably they use Maser clock, for example, not this kind of technology. So this kind of application might be, I mean, still worth publishing, I believe. Yeah. So there's one example. And or for example, if people are interested using the testing system, we may be able to, for example, fold some pulsar signal together, even with our existing antennas, for example.
Yes.
Yeah, that kind of thing may be worth working on.
Actually, I don't know if it will happen, but so galactic FRB was so bright, right? Was, if I remember, Mega Jansky level, if I remember. Therefore, while we are doing this test, then actually, if very bright FRB happen, then we may be able to detect. I don't know, but in such a case, maybe it's very fast.
I think we need a few tens of antennas for crab pulsar, for example. Or maybe we need to, like say, maybe fold it many times. Yeah. So for FRB, I'm not sure. Maybe it's because it's maybe one-off event, so it will be difficult to capture in the data. Maybe with maybe difficult, but for non-source, maybe.
Similar question. So how many antennas are needed to have a similar sensitivity as STER2? STER2 is a single dipole antenna at a similar frequency, right? So they could detect first galactic FRB since it's very bright. It has very large field of view. Otherwise, it is impossible. So how many antennas first do you need to detect galactic FRB?
Right.
Maybe we should see their sensitivity.
Yeah. Maybe. Let's see. I'm not sure if I.
Maybe if we can operate the system earlier with smaller antenna for a while, then maybe we still have a chance to detect brightest event in galaxy, our galaxy. STER2 is having very bad sensitivity.
Yeah.
It has huge almost spike on this cover.
STER2 is here.
So
So. Interesting. So this is roughly scale with, I mean, a number of antenna. It's very. So this is roughly scaling with a number of antenna. So this is 2,200. So 20 something like that. Yeah. So even single antenna supposedly. I'm not sure.
If you linearize here, do you linearize scale? Yeah, sorry. I wonder if when you calculate the effective area, I mean sensitivity, you just scale with linear number of antennas.
Yeah, that's right.
So that means
maybe so simply we need one.
why is one? Why is already more sensitive?
Only for very bright
Yeah.
event. But still they have a higher, they are occurring on the sky. So
But why STER2 is so less sensitive?
because the idea was so clever. That's why they realized just covering the whole sky is more effective to find such a brightest, very rare event.
So from 200 to 1, it's a factor of 200 now.
Yeah, roughly here.
Two order of magnitude smaller.
Yeah.
it is still better than which is better?
It also depends on the steer-to container sensitivity. It could be a bit different from maybe I'm not sure, but maybe the design is different from container. Apparently, the structure looks a bit different.
Oh.
Mm.
So that means we have a chance to detect very bright.
We always have a chance to have, if you have a very some number of type 1 antenna, it must be operating real time. So,
Right.
So maybe we can maybe use little by little once the operating system is
We have already chance.
Yes.
Mm.
So at the same time, this kind of event will be also always observed by STEP2. So maybe this is good. We have
Very interesting.
two telescopes
Yeah.
observing the same event.
Mm.
But I also see there's a 0.001 FRB per day.
That's yes.
So even if you multiply 365, you don't even detect one per year.
I think this is because this FRB is normal FRB at cosmological distance. So that's why.
This is
You mean this model lines? Yeah.
This FRB number, this FRB is they are shooting a very bright normal FRB at cosmological distance. But what STER2 detect is galactic distance intrinsically very fainter, but still bright for us because it's so close.
okay.
That's why. So that if we scale the rate with galactic FRB brightness, maybe we can have more. Maybe one.
So these numbers they are not looking at the galactic center, so not including galactic FRB. Is that right?
Yeah.
I think that STER2 operation year is also related, right? How many years they spend to
They only operated one. I don't remember, but I think less than 1 year.
Really?
I think it's so quick. Once they operate, they detect maybe, I think less than maybe 6 months. I'm not sure.
Really?
It was less than 1 year operation. They detect one first event.
That's good news, actually.
So maybe working on this quicker will be more effective in finding some maybe rare event. It's not FRB, typical FRB. So our kind of advantage is having a large field of view with higher sensitivity. So
Okay. That's very encouraging. Yes. Yeah.
it just depends how this kind of infrastructure is established. So how quick. Yes.
Mm. Yeah.
So that means when we start daily operation, so we already have chance to detect something and give it bright event happens.
Given the
Mm.
sensitivity.
So probably will happen when we have first FPGA at the site with 16 antennas and the real-time pipeline being implemented, and we have a good chance.
Hopefully we can detect something only during this pilot operation.
If we are lucky then.
Okay. All right.
So I have also a naive question about our group. So practically, how many people are working on the detailed issue? So I'm not sure. So how many? Of course, we should see the authors of the first proposal. But how many people are actually actively working on this, focusing on the first project?
So students, not many. I mean, right now mostly it's engineers, mostly working on the technical problems. So like the real-time process, there are maybe 2-3 people working, focusing on this kind of backend pipeline. Yeah, and then I'm working on the offline analysis, and then another engineer here, Homing, works on the FPGA programming. Yeah, and then several other people support the site development. Yeah, that's roughly 10 to 15 people altogether actively working on this project. Yeah, and also we're collaborating with the COSPA people who help us develop the site and as well as development new antennas. Yeah. 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 So actually, in terms of people analyzing the data, it's actually not enough people actually. Yeah. So we're actually hoping to get more people involved. Yeah.
So you need more people in the software part or
Yeah. Software part. Yeah. Okay.
So if students really want to join, then they can have desk here.
I mean, have a desk here.
Have a desk here.
I think should be able. Yeah, should be. There should be some. We can arrange. I think. Yeah. Yeah. But so practically, they think students can come here for a long time. Yeah. Okay.
Oh, okay. They can stay.
I mean, if they want, we should be able to accommodate them. Yeah. Okay. So, so I'm not sure what else we should discuss. So in terms of getting familiar with data analysis, we're thinking about one day or a couple of days data camp. The formats we still, maybe in person, so it's easier to interact. Yeah, but depends on, maybe we can talk afterwards on how to or when we can do this. Yeah.
Sounds good. So that is kind of practice for their competition. So.
Yeah.
I have a little bit more general question. Sorry.
Sure.
From that. So this is very technical, but if I remember, spectrum resolution is basically we assume the similar value as China.
Yeah, that's right.
It's probably kilohertz or.
I think for chime it's 0.4 megahertz, so it's
4 megahertz.
quite coarse.
So we also use that spectrum resolution.
Right, that's what we assume here. Yeah.
Okay.
So that FDMT, that bonsai example, let's use that spectral resolution.
If you go back to the raw data, so what would be the spectrum resolution?
So the pulse search intensity beam is integrated down to about 1 millisecond, but that's still longer, about 100 times longer than the actual spectral duration. So still several hundred spectrums integrated together. So in principle, you can have say 400 times more spectrum in one, and then spectral resolution is about 1 kilohertz. That's
that is our best effort.
1 millisecond, 1 kilohertz. I think that's about the maximum we can do. But whether it's sensitivity-wise, whether it's good enough, I'm not sure. Yeah. In terms of from sample to 1 millisecond time, there's a limit there.
a very general question because so this is really actually optimized for FRB detection.
Mhm.
But I was wondering if we can use it for other research. For example, SETI project
Mhm.
they use a similar strategy.
I see.
But instead of time resolution, I think, as far as I understand, they need a spectrum resolution a lot. Then we don't need time resolution, but
I
they
see.
need spectrum resolution. Therefore, I wonder if we can do that kind of things using burst.
You can do
Do that.
1 hertz. Yeah.
We threw away time resolution.
Yeah,
but
yeah.
We need a spectrum resolution for that one.
Should be, in principle, it's doable. Yeah.
Doable. But
Yeah.
we need to construct another backend.
Then the question depends on the maybe if we use the same hardware, say the FPGA, then let's see. Oh wait, it's a linear operation. So in principle, you can back out. I mean, you can recompute the increase the channel width after data is sent to a server. But then you probably need a lot of processing power for that process. So yeah, so, I mean, in principle, it's doable, but yeah,
Should be out of the box. I think. Oh, okay.
yeah, but need a dedicated hardware, I think, yeah. Dedicated server kind of hardware. Yeah. Okay. Questions from students? Okay. Yes.
Well, about the technical question. So maybe I missed some point. So I remember in the first beamforming, there's a data reduction to reduce the data size.
Mhm.
But in the second beamforming, looks like there's an upsampling from 8 bits to 32 bits.
Yeah.
So what happens, or why we do this reduction and then upsampling?
So for beamforming itself, we don't. So how to say? All the matrix operation, it happens with the more bit. If you only have 4 bits, then this multiplication is limited. You will lose a lot of information like phase accuracy, etc. So you're actually introducing noise if you have not enough depth, bit depth. So in the first beamforming, it actually happened before the bit reduction. So this is still happening when there are 14 or 16-bit depths. And then after the beamforming, then you do the bit reduction. But in a computer, when you do the second beamforming, it's also sampled. I mean, at least the matrix coefficient, etc. They are still using the longer, 16-bit depth. So the 4-bit is just saving the data transfer bandwidth.
So could you remind us what's the first and the second beamforming for different direction, or?
Yeah, for different direction, exactly. Yeah.
But is there any priority, or is just random?
You mean, do we want to prioritize north, south, or east, west? Yeah, assuming we have a square array, it probably doesn't matter. Yeah, so, but if we have, say, for example, in the outrigger station, we only have 64 antennas. Whether we want to put it as 16 by 4 or 8 by 8, there's a difference, right? And in principle, even if the one FPGA is processing 16 antenna, whether it's in one line or in 2 lines, 2 by 8 or 1 by 16, you can decide your complex coefficient accordingly. So in terms of computation, it's the same, I think. You just need to provide different beamforming coefficient. But initially, we probably use similar, if we want to speed up the design, then we probably choose 4 by 16 then we only need to worry about 1D beamforming at the time. Then I don't know whether we have a preferred, because if we have, I don't know, whether we have a preferred one. I mean, this is something we can still discuss. I mean, whether one is definitely better than the other. Yeah. If we follow Chime's example, they have more beams along north and south. That's one way. Yeah. But whether we have more beams in east-west is better. I don't. Right now, I can't answer right away. Yeah. But something still to discuss, I think. Yeah. Okay. Thank you. Okay.
Sorry, I forgot to ask. Actually, I wonder what kind of timeline do you plan? Say we have many components, and then do you have time schedule? So we need to finish this one until this. We need to finish this year or something like that. Do you have like a schedule? Then when maybe students want to try, then it's maybe important because they need to graduate, right? Therefore, this timing, if timing match their graduation, then that would be very helpful. So.
Yeah, it's I probably cannot answer you right now. Right.
Yeah, it's okay, but
Yeah.
it's good to have like a schedule.
Yeah. So I think we probably still need several months to develop the main sites and to deploy and testing. I'm thinking at least half a year to a year for the FPGA system to be operational at the site, and then more time to add more systems there. So my rough estimate is like main array maybe online in 1 to 2 years. Yeah.
You mean science operation may start in 1 to 2 years?
Yeah, probably.
Probably.
Yeah.
Actually, we can start from the very small
Yeah.
array operation.
Yeah. So initially, one FPGA may be operational half a year from now, something like that. Yeah. Yeah. But,
So related question. So is there any kind of any research students can do even before deciding the site, parallel to something for software analysis or software development? Do you plan something like this, or any study could be started right after the site decision?
Right. So I'm thinking that besides characterizing the sites, these kind of calibration steps needed to feed back to the real-time processing pipeline. That's something we need to study in parallel. So.
I will depends on the site piece.
Well, but the procedure will be applicable to different sites. Yeah. So the numbers will be different side by side, but the procedure should be similar. Yeah. I think that's something that is needed, and yeah, right away. Yeah. Yeah. Okay. And of course, when I say earlier, when I say mostly developing a site will be by our people, that's because we know how to set up, etc. But students are also welcome to join if you are interested, or for example, if the site is close to your campus, it's yeah, something you can in charge of maintain, for example. Yeah. And then, yeah. Okay. All right, so maybe any other questions for? Well, if not, then maybe you can officially finish and then some free discussion too. Yeah, maybe some people are more comfortable that way. Okay. Okay, thank you.
Thank you very much.
Thank you.